All right, so in this second lecture for this week, we want to do a mini organic chemistry review. And this is set up to really help you, again, become familiar with recognizing organic structures because all drug molecules are small organic molecules, or typically they are at least. So it's important to be able to recognize and draw organic molecules correctly. Recall that organic compounds are compounds that contain both carbon and hydrogen. They can be very complex and they contain many heteroatoms. So heteroatoms are defined as any other atoms in the molecule besides carbon and hydrogen. So there's some common heteroatoms that are found in organic molecules. These include oxygen, nitrogen, sulfur, phosphorus, and sometimes the halides can be found in there, with the most common ones being chlorine, bromine, and iodine. So because they're so complex, organic molecules can be drawn in several different ways, and you should become familiar with those different ways so that you can at least recognize what types of functional groups might be present. So you can have the molecular formula, and then you can have structural formulas and 3D models. These typically include displayed formula, condensed formula, and most common, we're going to be seeing line or skeletal formulas, and we'll sometimes see things in three-dimensional structures, including the ball and stick model or in a space-filling model. We'll also see how to abbreviate organic structures. So the molecular formula is the simplest way to represent a compound, and you essentially just count up all the different types of the atoms that are in the molecule and list them in order. So for example, our sugar glucose contains 6 carbons, 12 hydrogens, and 6 oxygens. So the molecular formula for glucose is C6H12O6. So by convention, carbon is listed first, followed by hydrogen, and then followed by oxygen, nitrogen, sulfur, phosphorus, and then finally any of the halogens that might be in the molecule. So the molecular formula really doesn't provide very much information. It doesn't tell you anything about how the atoms are joined together in space. So it's often possible, especially the larger the molecule gets, that two compounds can share the same molecular formula, but be totally different compounds because they're linked together in different orders. So molecules that have the same molecular formula, but have a different arrangement of those atoms bonded in space are called isomers. So we'll take a look at some of the common types of isomers that exist and how to start recognizing those. This can be very challenging, so don't get discouraged if it takes a while to be able to recognize and see isomers. So here's an example of two different isomers. These are sugar isomers, and they both have the molecular formula C6H12O6. And you can see we've got glucose. So again, 1, 2, 3, 4, 5, 6 carbons. And then you can see that fructose also has those same 6 carbons. 1, 2, 3, 4, 5, 6. But you can see that the bonded order is different. You have a double bonded oxygen at that first carbon position, but you don't up at this carbon position. The double bonded oxygen is now at the second position. Because these atoms are arranged differently in space, these are said to be isomers of each other. So in addition, we can see another representation of our molecules here from the molecular formula. When you have all of the atoms represented and you're showing their arrangement or connection in space, these are called displayed formulas. So all of the bonds have individual lines with each atom written at the end of the line, right? So here you've got a carbon-carbon bond, and at each end, the atoms are written. So this is a displayed formula. Everything is very apparent in here. So the only thing that the displayed formula doesn't really give you, it doesn't give you the three-dimensional angles that are represented in the structure. So in the center here, you have methane, and you've got the displayed structure. So you just have lines representing each bond out to each of the hydrogens. However, the molecule itself is not flat, it's not planar and two-dimensional. It has three-dimensional structure in space. And so the ball and stick model that's shown here and the space-filling model shown over here are better representations of that molecule in three-dimensional space. So this can be very useful for medicinal chemistry because it really shows you the shape of larger molecules, especially when we get into drug targets, which can be protein or DNA, and other very large molecules that are found inside of cells. So that can give you kind of the lock and key that our small molecule actually has to fit really perfectly inside a protein. So these are very useful representations looking at three-dimensional structure. So in these model types, and you may remember this from using model kits in organic chemistry, carbon is always shown as black, hydrogen as white, oxygen is red, nitrogen is blue, and sulfur is often shown as yellow and phosphorus is orange, but sometimes phosphorus is also shown as yellow, so you just have to be a little careful with those two. And then typically the halides are always represented as green atoms. So that could be a chlorine, a bromine, or an iodine. They may all be represented as green. So notice when we have our displayed formula, again, it does not indicate that three-dimensional shape, right? So if we write out our molecule here with 2 chlorines and 2 hydrogens, we can also write it like this, with the 2 hydrogens kind of next to each other over here and the 2 chlorines next to each other over here. However, even though we're writing them different in the two-dimensional structure, these molecules are exactly the same. So these are the same molecule. They may look different, but they're both representations of dichloromethane, right? And so if we look at this in three-dimensional space, this becomes way more apparent that no matter kind of how you turn this molecule, you can see the representation here of the 2 hydrogens in white in the back over here, and then the 2 chlorines represented by the green atoms in the front in this side, but then kind of twisted to the back in that side. So you kind of have to start wrapping your mind around the three-dimensional models to really look at something in 2 dimensions. So remember, even though you can draw things in the displayed formula in 2 dimensions, the shape can be very different. And so this can be difficult to kind of look at at first. So this gets to an important component of the carbon atom. Carbon forms tetrahedral geometry. And what that means is that each of the bonds connected to the carbon, so carbon will make 4 bonds, remember, to get to fill its valence shell. And each of the bonds around here are at 109 degrees, right? This is as far apart as these bonds can get from one another, right? And so this is because the electrons, right, that are being shared across the bond, right, they repel each other, right? The electrons are negatively charged and they want to be as far apart as possible. And that happens to be 109 degrees away from each other. So this is called valence shell electron pair repulsion, or the VSEPR theory, is that electrons want to be as far away from each other as possible because they're all negatively charged and they repel each other. So this gives the tetrahedral geometry that is common to the carbon atom and that structure that you saw in the last slide. So all of the carbon centers that are bonded to 4 different things have that tetrahedral geometry. So this is a little bit more complex molecule. You can see it contains 1 chlorine, and all of the other positions around the carbons are hydrogens. They're all going to be the same molecule. So these are all identical, right? And if we look at this in space, we can see as we rotate this around that, that we can shift and rotate the molecule, and these are exactly the same. So as you continue to practice drawing out the structural formulas, you'll become better at recognizing or distinguishing between real isomers, true isomers, that are truly different from one another, and versions of the same molecule that are drawn from different 3-dimensional perspectives, like the one that we just looked at. Okay, so that brings us from displayed formula, which shows every atom inside the molecule, to more condensed formula. So because organic compounds can be so big and bulky that drawing them out in displayed formula becomes really tedious really quickly if you have a super large molecule, right? So we want to start getting more and more condensed and really showing kind of less and less of the molecule, right? So a displayed formula shows each bond with each atom at each end of the bond, but you can condense those down, right? So we know we've got a carbon here that's bonded to 3 hydrogens. So we can condense it to a CH3 group, and we can infer that each of those hydrogens is bonded to the carbon just like this, right? So this is a partially condensed structure. We've condensed down the hydrogen bonds when they're bonded to things, but we've kept some of the bonds from the carbons coming out. So that's partially condensed. A fully condensed molecule will condense the bonds even further. Notice, though, that in the condensed model, this can get a little bit confusing, right? Because in this situation, we have our carbon bonded to 2 different oxygens, 1 oxygen with a double bond and 1 oxygen with a single bond. But here in this condensed formula, you can't really tell if the carbon is bonded to each of these oxygens, like it is in our partially condensed structure, or if the 2 oxygens would be bonded together, right? Like making a bond more like that, right? In a peroxide type of thing, right? So it could be like that, or it could be the way it's written out here. So fully condensed formula are not as useful as the partially condensed, in which you know exactly who is bonding to who, right? So when you have fully condensed structures, there may be more than one way to hook them together. So ultimately, it can be very challenging to accurately see the bonding patterns when you have those fully condensed structures. So if you have a condensed formula, you can work backwards to try to connect them back together. So you'll notice this first carbon, you have to remember the rules of carbon. It needs 4 bonds per carbon, okay? Rules of hydrogen, it can only have 1 bond per hydrogen, right? And rules for oxygen, it needs 2 bonds per oxygen atom. Okay, so with those rules, we can start looking at condensed formula and trying to build them back out. So we can see that this carbon, right, is bonded to 3 hydrogens. That takes care of 3 of the 4 bonds. We know then that it also must be bonded to that next carbon to make its 4th bond. So we could start drawing out, right, this structure. We could say, okay, into a displayed structure, we know those 3 hydrogens are bonded to that. And then that next carbon over is bonded to that carbon as well. We know that these oxygens, however, are not bonded to the first carbon because it's full now. It's got all 4 bonds, right? So we need to start placing around the oxygens, right, to this center carbon. The hydrogens are all used up, right? And they were shown next to the other carbon. So we know that this carbon needs to have 4 bonds, right? So if we wrote it like this, right, with the 2 oxygens bonded together, right? The oxygens are happy. They each have 2 bonds, but this carbon is very unhappy. It only has 2 bonds to it. So that's not likely the correct structure, right? So if we're looking at who's bonded to this carbon, we know that each of these oxygens is likely going to need to be bonded to that center carbon to help fill out those bonds. And because this hydrogen is shown last, it's bonded to whatever it's next to, which is going to be that last oxygen. Right? So instead of building it out like this, where you have the oxygens are happy, but this carbon only has 2 bonds and is very unhappy, we need to set it up more like this, where this again is bonded to that carbon, and then that each of these oxygens is going to be bound to that carbon. We then bond that last hydrogen to its next door partner, which is that oxygen. And we can see we now have 3 bonds around the carbon, happier, not happiest. And we only have 1 bond around this oxygen, not happy either. So we still have a situation where that's not happy and that's not happy. So we're going to end up needing to form a double bond in here to make that final carbon happy and the oxygen happy. So that's going to be our solution for this problem. 2 of the lone pair electrons from that first diagram are going to fall in to form a double bond. Right? And now this carbon has 4 bonds. This carbon now has 4 bonds. This oxygen has 2 bonds. And this oxygen has 2 bonds. And this hydrogen has 1 bond. Everybody is satisfied and happy. So this is the correct or most likely structure. All right, so we won't do too many condensed formulas and make you write out those things, but you will see methyl groups or CH3 groups. So these are called methyls. You will often see those written out as CH3 in molecules, right? Or we can move to a line structure. Line structures are going to be very common. These are also called skeletal formula. And in these situations, all of the hydrogen atoms are not shown. So they're all implied. In addition, all of the carbons are not labeled, but they're going to be indicated either at the end or a bend in every line, right? So if we're looking at the molecule over here on the right, this guy is the skeletal drawing. We can see every end or bend is going to represent a carbon. So I know I've got 4 carbons in this molecule. So everywhere I have a bend or an end, that is a carbon. And I know carbons have to have 4 bonds. This one I can see 1 bond from one carbon to another. That means I have to have 3 more hydrogens that are implied to fill that guy up, right? I can see this carbon, right, is bonded to this carbon, to that oxygen, and to this carbon over here. That's 3 bonds. So it has to also have 1 hydrogen that's not shown but implied. This carbon is bonded to this carbon over here and this carbon over here. That's 2 bonds. It needs 2 more bonds to be happy. So there has to be 2 hydrogens there. And then this carbon bonded to 1 carbon needs 3 hydrogens to bond in here. All right, so that is our line structure or skeletal structure. Any heteroatoms have to be shown, and their hydrogens always shown. Okay, so they always have to be shown. So this is a summary of those line and skeletal formula. There's a carbon atom at each line junction, and at the end of each line, there are enough hydrogen atoms attached to each carbon to make the total number of bonds on that carbon equal to 4, and all heteroatoms and hydrogens attached to the heteroatoms are shown in the condensed format of the skeletal structure. So those are our overall rules for our line and skeletal formula. You will be responsible for knowing and understanding that in any drug molecule that you would see in this class. So there are also ways in structural formula to show three-dimensional shape, and that's by using the wedge dash system, right? So anytime that you see a straight bond, that's going to indicate that it's in the plane of the paper. If you have a wedge that's dashed, that means the bond is going back into the paper away from you. And if you have a solid wedge, that means the bond is coming out of the paper toward you. All right, so this is an example of a partially condensed structure for 2-butanol shown up here. Again, that doesn't give you any information about the three-dimensional structure. So when you actually draw this out, you can see that these bonds are in the plane of the paper, but then you've got a CH3 group going back into the paper, an H group going back into the paper, and the forward wedge here coming out of the paper at you, right? So this shows the tetrahedral nature of that carbon atom. Right? It's got 109 degrees between each of these bonds. Right? So you've got that tetrahedral structure. And then you can see something unique happens here. You can see that on this side, you actually develop isomers of one another. Right? So these guys are mirror images. So if we draw our mirror right there, you can see that these are mirror images. And if we tried to superimpose this one on top of this one, if we rotated it, right, and put it down on top, we would see that the CH3 and the H group would come out of the paper towards us, and the OH would go back into the board, and we could not superimpose these. So these are mirror images, but not superimposable. And so these are isomers of each other. So these are true isomers. And when they're exact mirror images, but not superimposable, the name of those isomers are called enantiomers. Okay? This becomes very important in our discussion of drug compounds because drugs interact with proteins and they are like a lock and key fit to them. And so if you have one enantiomer, it's like having the left-handed version of the molecule versus the right-handed version of the molecule. And only one is going to fit into the keyhole. The other one would be the wrong shape, right? It's going to bend in the opposite direction and it won't fit into that same lock. So if we're thinking of our drug molecules as the key, our lock is going to be very specific for that shape. All right, so another thing that is also done in organic chemistry is organic chemists like to abbreviate structures that may be repeated a bunch or may be unique to a drug molecule, and then they only show the base and then they show the R groups down below. So when they are abbreviating an organic structure, they use a generic term, and this is R. So R can really be anything with a bunch of carbons in there, right? So you have to define what R is going to be. So in this diagram, R can really be anything. It's not defined. So it's not defined here, right? So it could be any carbon-containing compound. All right, so if it's not defined for you, you have to think, well, it's something carbony over here. I don't know what it is. So here's an example of when R groups might be used, right? So in this case, you've got a framework for a drug, and this is the framework for penicillin, right? And they have shown the R group up here. So for actual benzyl penicillin, the structure of benzyl penicillin is going to have a benzene ring structure, which we'll talk about more here in a few minutes, right? And that will be the R group, right? So the R group is shown in red here. And then you can see another couple of common antibiotics are ampicillin and amoxicillin. You may have taken these before. They're both clinically relevant and used. But you can see that they differ in their structures only slightly from the benzyl penicillin, right? There's another nitrogen functional group up here. And for amoxicillin, there's also an OH functional group. So here, they're defining the R's for you for very specific compounds, here, here, and here. And instead of redrawing the entire penicillin framework every time, I can show it to you once up here, right? And then you can fill in the R group as needed for which drug compound you want to be talking about. So this is a very common way in medicinal chemistry to represent drug molecules. And there is a note or a caveat. As a rule, you should never abbreviate any atom that's involved in a bond breaking or bond forming event that's being illustrated with a compound. So where the chemistry is actually happening, you don't want to abbreviate that or hide it in an R group, right? That needs to be shown. Okay, so we've talked now about isomers, that they have the same molecular formula, but they have different arrangement of the bonds in space. And so how can we recognize that? Well, we want to get into this concept of chirality, especially for our carbon atoms, right? So again, the molecular formula is often insufficient for defining the compound, as many molecular formulas have numerous structural isomers, right? So for a C2H6O molecule that only has 9 atoms, this can refer to dimethyl ether or ethanol, depending how you put them together in space. So structural isomers have the same molecular formula, but the order of the atoms linked in space is different. Okay, how about our sugar molecules? We saw glucose and fructose last time. Now we're seeing 2 different sugars, glucose and galactose, right? These ones only differ in one position, right? So if we're kind of drawing like a mirror down here, again, our symmetry plane. So this is a symmetry plane or a mirror, essentially, right? We can see that this oxygen and this oxygen are on the same side. We can see this oxygen and this oxygen are on the same side. But we can see this oxygen and this oxygen are mirrored to each other, right? So they're like a reflection in a mirror. These ones are different in their arrangement in space, right? But we can see this one and this one are on the same side. And then you can see there's abbreviation down here, and we're showing partially condensed structure. And then this one is not really indicated either. So this one is the stereocenter, and these guys are different. But why are they different? Right? This gets to this concept of chirality. So carbon will show isomers if it's bound to 4 different constituents. Okay? And so this is our definition of chirality. It is said to be chiral if you have 4 different constituents. If it doesn't, if it has 2 of the same constituents, right? So if 3 or less, then the carbon is achiral, right? So I tend to say when I mean achiral, right? That is like if you're amoral, you lack morals. If you're achiral, you lack chirality when we're talking about carbon. I usually, because you could say that carbon is a chiral center, it gets really confusing. Do I mean achiral or do I mean a chiral center? Right? So I tend to not say this word. I don't like saying achiral. I like saying that carbon is not chiral. I don't think you ever get confused when I say that is not chiral versus saying that carbon is achiral, which are the same things, right? So achiral means not chiral, but I won't really ever say that. I will say that carbon is not chiral. And how can you tell? Well, if I look at this carbon up here, it is bonded to this oxygen twice and one hydrogen and one carbon. It's only bonded to 3 things, right? So this one is not chiral. It is not a stereocenter and it won't have stereochemistry around it. However, if we look at this carbon center here, it's bonded to hydrogen. It's bonded to that OH group. It's bonded to this C double bond OH group. And it's bonded to this giant thing down here. So that carbon has 4 different things bonded to it. This carbon here is chiral. So this one is chiral, means it is a stereocenter and will have isomers related to it, whether it's back and forth, right? So that's locked in a position where you can't superimpose it on top of the mirror image, right? So this is the same situation down here when we're looking at this carbon center. So it's bonded to this giant thing up here. It's bonded to one hydrogen. It's bonded to one OH group. And then it's bonded to this large piece down here. All of the fragments are different. And so this carbon center is also chiral and has stereochemistry about it, which means it won't be superimposable on its mirror image, right? So these are not facing in the same direction. So these 2 molecules then, glucose and galactose, they only differ at this one position, but that's enough to make them different sugars. They have different properties inside the body. They're a different key for different locks, right? So different enzymes will be able to tell the difference because their shape in space, in 3-dimensional space, is different. So these are called stereoisomers because they differ around that mirror plane. This is different than structural isomers where the bonded atoms are in a different order, right? So the bonded atoms are in the same order. This carbon is bonded to an oxygen, a hydrogen, this big lumpy thing up here, and this big lumpy thing down here. And the same for this molecule as well. A hydrogen, an OH group, the same big lumpy thing up here, and the same big lumpy thing down here. So the bonded order is the same, but the mirror image is different. So these are when you have a stereoisomer occur, right? When you have that mirror around that symmetry plane, and those molecules now are not superimposable on each other. So this is a stereoisomer. It's not an enantiomer because all of the positions would have to be mirrored for it to be the enantiomer, the direct mirror image, because this position is not a mirror, this position is not a mirror, they're the same, right? This position it doesn't matter because it spins, it doesn't have chirality. And this position down here, if we look at this carbon, it's bonded to 2 hydrogens, right? So that's 3 or less different constituents. So this carbon down here is also not chiral. It does not have stereochemistry about that carbon. Okay, this is a hard concept And when we talk about chirality and stereocenters and different isomers in this class, you will get better at looking at these molecules the more that you see them. And so I will try to point these out when we're really focused on the isomers and chirality of our drug molecules, because it does make a difference. You can oftentimes have two different stereoisomers of the same compound, or the enantiomers of a compound that might be present in a drug system. Okay, so glucose and galactose are very similar to each other. They're going to have very similar physical properties to each other as well. And so they're going to be hard to separate from one another. And when you have the enantiomers, it becomes even more difficult because they're more alike each other. So sometimes it can be really, really challenging or difficult to get two mirror images or enantiomers to be purified away from each other. And that can be a problem when we're thinking about drug molecules. Okay, so we said when you have exact mirror images, right? You're looking in the mirror and across the way you see yourself, across the way you see yourself, across the way you see yourself, but you can't superimpose this molecule on top of itself. This is chiral, right? Because it's bonded to four different things. It's bonded to the CH, the OH, the H, and the CH2, CH3 group up here. Four different things, right, equals chiral, right? And so this has an isomer. It has this mirror image in this case that we're seeing here. So these guys are called the enantiomers, right? So enantiomers, again, are the mirror images of each other, but they are not superimposable on top of one another. All right, it's just kind of like your left and right hand, and you can hold them up to each other, and you can see that they are mirror images of each other, but they're not superimposable. If you try to put one hand on top of the other, the thumbs are on the wrong side, and so are all the fingers. They are chiral too. So your hands are chiral, your feet are chiral, right? They have mirror images of each other that are not superimposable. Your left hand is not the same as your right hand. Carbon is chiral when it has four different groups bonded to it, and we've been getting practice at looking at that. So when you have a chiral center, you can have a mirror image that is not superimposable, and this is called the enantiomer. All right, so we've already talked about enantiomers, and we've seen this one now several times. They have the same chemical and physical properties, except the way that they will rotate plane polarized light, right? So if we shined light only moving in one direction down on these molecules, right, it would rotate that light when it hits it in opposite directions. One is going to rotate it left, and one will rotate it in the right-handed direction. And that's really the only difference. So both of these molecules are given the same name. They're both 2-butanol. Okay? So this is why we've developed the Cahn, Ingold, Prelog priority system to tell the difference between enantiomers. Okay, so this was designed to determine the absolute stereo configuration of the enantiomers as sinister, S, or rectus. So in this system, the groups attached to the carbon are given priority ratings based on atomic number. The higher the atomic number, or more protons an atom has, the higher the priority. So sulfur is the highest, phosphorus, then oxygen, nitrogen, carbon, and hydrogen at the bottom, right? So you can determine which has the highest priority, and you can determine the stereo configuration around an enantiomer. Okay, so we have a stereo center here, right? And you can see there's 4 different groups that are attached to this. So this is a stereo center. It has chirality. We can assign priority to each of these, right? There is a carbon here. You go out to the first position. and there is a carbon here. The carbons are equivalent, right? And we have an oxygen up here, which is higher atomic number, and hydrogen is last. So this is lowest priority, and this is highest priority, right? So we can assign this as number 1, and we can assign this as number 4, because there's 4 things attached to it. So now we have to determine between this position and this position as the number 2 position. Well, so we go out to the next layer, and we can see this carbon is bonded, right, to 2 hydrogens. They're not shown, it's a line diagram, but they're there, and 1 oxygen. This carbon is bonded to 1 hydrogen and 2 oxygens because it's double bonded to this one. So this one gets higher priority as the number 2, and this is the number 3. So when we're rotating around here, we're rotating in the clockwise direction. This is the R form. Okay, so we saw this situation here. It's rotating in this direction, 1, 2, 3, and 4. This is the R designation for glycerol, or the molecule that we just looked at, R-glyceraldehyde. Clockwise equals R configuration. If we're going in the counterclockwise direction, right, we can see the positions again. We said that oxygen is position 1. We said, in this case, the carbon that's bonded to the second carbon, that's position 2. We have a carbon over here bonded to 3 hydrogens, that's position 3, and 1 hydrogen, position 4. So this is going in counterclockwise direction. That's the S conformation. And we can see this one is priority 1 here, priority 2, 3, and 4. This one is the clockwise direction, or the R conformation. So they're different from one another. And always in the CIP configuration, it's helpful to hold the 4th position in your hand. So if you had this molecule in your hand, you hold that hydrogen, which is the least priority, and then you look at the face of the other 3 that are coming out at you, and you can see the rotation and priority that way. So why are enantiomers so important? Well, distinguishing between them is critical for the drug activity, and in this case, a hideous side effect with the wrong enantiomer. So this drug thalidomide was provided mainly as an anti-anxiety medication, and women were commonly taking it. It was approved over in Europe. It actually wasn't approved in the United States, which that's good. But you can see that there is a stereo center in this molecule here, right? And so in this case, the nitrogen is going back into the plane of the board and the hydrogen is coming out. And in this case, the nitrogen is coming out toward you and the hydrogen is going back into the board. This is the effective isomer. This is a horrible mutagenic isomer. And so what happened is that they thought the thalidomide was fine. And if women took it, there was no problem with it. It calmed them and, they had less anxiety. However, if they were pregnant and they were taking this drug was a mixture of both isomers. Because it was so hard to get them apart from each other, they didn't purify them away from each other so that you only would have the effective isomer. It was a mixture of both of these things, and those poor women and their poor children ended up having horrible mutations that occurred that would deform their arms and their legs and just have these horrible birth defects that happened to them. So this happened to 10,000 babies before they were able to stop it and pull this off the market. So this gives you a very disturbing example of why distinguishing enantiomers is very important when we're thinking about drug compounds. So when you have a drug molecule that has a stereocenter that has two enantiomers that are in it, and when they're so alike in their properties that you can't separate them from one another, what you end up getting is called a racemic mixture. This means it has at least two isomers in the mixture. And these are the enantiomers, the mirror images, okay? Thalidomide then is a racemic mixture of these two enantiomers of one another. We said a protein then, the target protein, right, is going to bind to a specific chiral molecule. It is like a key, right? So the other form, the other stereoisomer, will not really bind to that protein, right? It's going to be in the wrong shape, right? And it won't fit into that lock and key. But it doesn't mean that it won't bind to anything inside the body, right? There are lots of things inside the body, and so the other enantiomer can go around and wreak havoc in some instances or cases and cause, again, with thalidomide, those terrible side effects in a developing fetus. So this tells us that proteins are stereospecific. They are like a lock and key, and when you have the wrong enantiomer, you're not going to put, a square peg in a round hole. So there are current racemic mixtures that are sold on the market that we use. Ibuprofen is a good example of this. So it's given as a racemic mixture. The R version is inactive. The S version is the active enantiomer. But anytime you take ibuprofen, you're getting both. And again, that is because it is so difficult to separate these out. Okay, so I just want to end this mini review with common organic functional groups that you'll need to be able to recognize. So functional groups are specific atoms, ions, or groups that have consistent properties, and they make up the overall larger molecule. All right, so alkanes by default are the simplest types of organic molecules. They only have carbon and hydrogen bonds, and they only have single bonds between the carbons and the hydrogens and the carbon-carbons in there. Alkenes, on the other hand, with the E in there, have at least one double bonded carbon in the molecule, and alkynes with the Y in there will have at least one triple bond. All right, so alkenes and alkynes are unique because when they're doing their bonding, if you'll remember kind of pi orbitals and s orbitals from your shapes, right? The double bond is using pi orbitals, which kind of extend up and down from the atom. And so that second bond, right, it's like a propeller on a plane. If you twist the bond, you're going to move the propeller on one side, like you would move it down, and then those electrons won't be able to be shared between the atoms anymore. So the double bond is fixed. It can't rotate, right? And so this introduces stereochemistry around that bond, right? So if you have the two methyl groups in this case, they're both on one side of the double bond. That is a different molecule than having the methyl groups on either side of the double bond. In this case, when they're on the same side, it's called cis conformation. And if they're on the other side of the double bonds, the functional groups, this is the trans conformation, right? So double bonds, and you can see this in the shape of the molecule, right? So again, you can draw a line down the double bond, and those functional groups are on the same side, or you can draw a line down the double bond, and now your functional groups are on the other side of the double bonds. So same side, cis, opposite side, cis-trans, and we will see structures that have this cis-trans stereochemistry to them. So all the alkanes, alkenes, and alkynes are classified as hydrocarbons because they only contain hydrogen and carbon. The alkanes are said to be saturated with hydrocarbons. So when you hear a term of saturated fatty acids, they're going to be saturated with hydrocarbons. They don't contain any double bonds or triple bonds in them when you have a saturated hydrocarbon. If they're unsaturated hydrocarbons, that means they have at least one double bond position or one triple bond position in them, and they will have fewer hydrogen atoms then bonded to them than a saturated hydrocarbon of the same carbon length. Okay, our next functional group is the aromatic group. So you can see aromatic groups are 6-membered rings. So they have 6 carbons in here. And they form this nice hexagon, and they have alternating double bonds. So one double bond, one single bond, one double bond, one single bond, one double bond. That is an aromatic group. So you can't really tell, like, these are shuffling around in this molecule. As it's just sitting there, that double bond will kind of flip. It can't really tell the difference between the different carbons. And so you can draw your benzene ring, right? This one is drawn with the alternating bonds here, but the same structure can also be drawn with the bonds in the other positions, and it's the same compound, right? You can't tell the difference between those two, right? Because you're just shifting the position of the double bond. And so these are called resonance structures. And the molecule is actually bouncing back and forth between the two structures, right? Those double bonds are kind of constantly shifting shape. Again, because the electrons in this bond, they really can't tell the difference between this carbon and this carbon and this carbon and this carbon. So they're going to want to keep popping around and sharing in different ways. So you can represent the overall aromatic structure. You can just draw a circle in it like that. And so sometimes you'll see that it written like that as well. And this is showing the overall resonance structure. So it means both of those things together. All right, so alkyl halides are just going to have a carbon that has a halide of some kind in it. So halide, remember, are group 7 elements, right? So this includes anything in that last row that starts with the fluorine and drops down: fluorine, chlorine, bromine, iodine. All of those things are halides. So you can call it an alkyl halide or a haloalkane, depending on which you put first. You put the alkane first, the carbon-hydrogen bond. The halo is the prefix, that's the halide. Or if you want to emphasize the halide, then the alkyl becomes the prefix. This brings us to alcohols, phenols, and thiols. An alcohol functional group has an OH group. So it's a carbon single bonded to an OH functional group. When this is part of a larger molecule, the alcohol is called a hydroxyl group. Primary alcohols have one carbon bonded to the carbon that has the alcohol. So there's a primary alcohol, right? A secondary alcohol, right, has 2 carbons bonded to the carbon with the alcohol. And a tertiary alcohol has 3 carbons bonded to the carbon with the alcohol group. And these have different reactivities depending how much hydrogen they have associated with them, with the more hydrogen being more reactive typically. Our phenol is an aromatic group with one of the carbons bonded to an alcohol. And then the thiol, you'll recall that sulfur is below oxygen in the periodic table, so it has similar properties to oxygen, but it's a little bit bigger. And so the SH group is called a thiol. All right, so those are alcohols, phenols, and thiols. Just to be clear, for the phenol, the alcohol group has to be directly attached to the ring structure. So in this case, this is not a phenol, right? It is a primary alcohol, right? Because this one, this carbon has two hydrogens and one carbon attached to it. So this is a primary alcohol and an aromatic group, an aromatic ring. Then we get to ethers and sulfides. These are oxygen or sulfur that's trapped between two carbons, right? So there's two carbons here, makes the ether. Two carbons here, makes the sulfide. So a sulfide can also be called a thioether. Thio refers to sulfur. Anytime nitrogen is in a compound or attached to carbon, they are called amines. The simplest amine is only attached to hydrogen and is ammonia. So for amines, primary, secondary, and tertiary amines are defined a little bit different than our alcohols. It's going to look at the carbons that are bonded directly to the nitrogen itself. So in a primary amine, the nitrogen is bonded to one carbon. In a secondary amine, the nitrogen is bonded to two carbons. And in a tertiary amine, the nitrogen is bonded to three carbons. So don't get that confused with how you determine primary, secondary, and tertiary for alcohols. For the alcohols, you're looking at the carbon that's bonded to the oxygen, right? So this is a tertiary alcohol, right? Whereas an amine, you're looking at what is bonded directly to the amine. So this is a primary amine, right? Because it's bonded to one carbon. You're not looking at the carbon and who the carbon is bonded to, like you do for the alcohols. Amines can act as a base. They have basic properties, right? So if we look at our simplest one, right, if we're looking at nitrogen, you'll recall that nitrogen has a lone pair of electrons that are associated with it, right? So it will attract a proton, right? So if there is an H that's missing its electron, right, it is an H plus, and that is our definition of an acid that we will review later as well, right? This H plus is going to be attracted to that partial negative charge that is on the nitrogen, right? And so this forms an ammonium ion. And when it pulls that proton out of the solution and associates it with the nitrogen, it's removing protons, right? The protons from the solution. And so this means it's acting as a base because the protons, right, are acidic. So if you remove them, then the solution is less acidic, right? So you can have a primary ammonium ion that's charged all the way up to a quaternary ammonium ion that will be charged. Okay, just a few more and then we'll be done. Phosphate groups are also important. We see these a lot in DNA molecules. A phosphate is a phosphorus atom bonded to 4 oxygens, and 3 of those oxygens are in a charged state. So the PO4 molecule has a negative charge. You may recall these as polyatomic ions when you were building these in general chemistry or in chemistry 103. You could see that these could form interactions with metals like sodium, right? Well, phosphates are very common in biological systems. You can form a phosphate anhydride where you hook 2 of them together. You can have phosphate esters, right, where you connect one of the oxygens to a carbon, and we'll talk about regular esters here in a minute as well. And you can have a phosphate diester, and this is often just called a phosphoester, or in this case, the phosphodiester, because there's 2 of them, right? And this is the common bond that ends up forming in DNA. you've got phosphodiester bonds, which you may have heard of as well. All right, and we have aldehydes and ketones. So if you have a carbon that's double bonded to an oxygen, if it has one hydrogen and one carbon attached to it, that's our definition of an aldehyde. If it's trapped between two carbons, it's a ketone. And then the carboxylic acids and their derivatives. So if you have a carbon that is double bonded to oxygen and also contains an alcohol group, this is the definition of a carboxylic acid. It's an acid because that hydrogen will want to come off, right? And it will come off as H+. It will leave the electron with the oxygen. And so when that H comes off, the resulting ion that forms is a carboxylate ion and the proton, right? And this is a definition of an acid, right? Is when you have more protons in solution than OH groups. So that's the acidic proton will come off. The carboxylate anion is left. You can also make esters. Carboxylic esters, right, would put a carbon on there. You can make a thioester by substituting in a sulfur in there. And you can make an amide by substituting an amine in there as well. So anytime you see nitrogen next to a carbon that's double bonded to oxygen, that's an amide. If you see sulfur next to a carbon and double bonded oxygen, that's a thioester. And if you see carbon and oxygen next to a carbon double bonded to an oxygen, that is your standard ester. You could call it a carboxylic ester. You don't really have to say that. If you just say ester, this is what you mean. All right. And then these last two slides just show you a summary of what we've been talking about. There are some special functional groups that you see here. We are not going to talk about these in depth now, but we will be coming back to talk about things like epoxides. That is a 3-membered ring with oxygen, very reactive, right? Very strained, right? Whoop. And very reactive. So that will be something that we may see in some drug compounds that give them their reactivity. Nitriles or cyano groups are also quite reactive. Acid chlorides, very reactive. Azides, also very reactive. So this page is really showing more biologically active groups. And we may see some examples of these inside the class as we're going through drug compounds. All right, and so that is where I'd like to stop with our mini review of organic chemistry.